All right, welcome back to Physics 221. This is Chapter 39, Wave Functions and Uncertainty. So this is still quantum mechanics. I'm sure you realize by now that quantum mechanics is just very mathematical, and you'll see that today. I wrote a note to myself last time I taught this class. This chapter will be used extensively in the following chapter, Chapter 40. So the students must learn it well. So just be aware of that. Just think of back in Physics 121, you learn how to draw force diagrams, and then the next chapter you had to solve force problems. But if you couldn't do a force diagram, you couldn't solve a force problem. So this is similar. If you don't understand Chapter 39, Chapter 40 is going to be just a disaster. All right, so be aware. All right, so wave functions, which I already talked about a little bit, and uncertainty. We're going to introduce the wave function as the descriptor of particles in quantum mechanics. We'll provide the wave function with a probabilistic interpretation. That's quantum mechanics, probability. To understand the wave function through pictorial and graphical exercises, to introduce the idea of normalization, to recognize limitations on knowledge imposed by the Heisenberg uncertainty principle. All right, so we're talking about light again. So let's review the wave model and then the photon model. So for the wave model, as usual, we'll talk about the double slit experiment. So you remember this from the wave function, the wave chapter. We have a wave here, a wave there, and they interfere, and so the net displacement was just the sum, and we added these two traveling waves, and this was the answer, and this is the amplitude of the wave, which we just denoted as A, and as a function of x. All right, so the amplitude, 2a cosine pi dx over delta L. Whatever. Okay, and there's our nice, it's really an inverse sign. Here's a nice sinusoidal amplitude. So that's the interference pattern that you get from the double slit experiment. Now, here's the question. What do you see on the screen? Do you see this? Or not? I mean, do you see this? You have a negative and a positive and a negative? Of course not. You can't see that on the screen. So what you really see on the screen, you see the intensity of light. The intensity of light. Where the intensity of light, remember, for a wave, is equal to amplitude squared. So you get 4a squared cosine squared, blah, blah, blah. All right, so there's your little review of the wave model of light. Now let's talk about the photon model. And again, we're going to talk about the double slit experiment. So we're shooting light through two slits. At first, we just see the individual specks. We wait longer, we see more specks of light. We wait a really long time, and we see an interference pattern. All right, here's a question for you. The figure shows the detection of photons in an optical experiment, like I just described. Rank in order from largest to smallest the square of the amplitude function of the wave at positions A, B, C, and D. So let me give you a hint. What's the square of the amplitude function? It's the intensity. All right, so students, pause your video and figure it out. Okay, so I hope you realize that you have more dots here than anywhere else, so this is the highest intensity. This looks pretty much the same as that. So A is the winner. It looks like D and B are tied for second, and C is definitely last. So there you go. All right, now the question is, we have this wave model that works and it describes data, correctly. We also have a photon model that works and it describes data correctly. So what we want to do is we want to incorporate both models. How are we going to do that? Well, believe it or not, in order to do that, we have to review probability. So we're going to review some elementary probability. All right, so here is a target, and this is region A, this is region B, and region C extends to infinity, okay? So just pretend that this gray area extends to infinity, all right? All right, so you can see there's 45 darts or whatever holes in region A, 35 in B, and 20 in C. Okay, so this is how we define or discuss probability. We say, and this is a technical definition, the probability that a, let's say arrow or dart, I don't care, arrow will land in A is the limit as n total approaches infinity, the number in A divided by the total number shot. All right? So that's really the definition. And you can say the same thing with, you know, for B, you put a B here and a B here, and C, you put a C there and a C there. Okay. Now, come on. In the real world, you don't usually have n, you know, equals infinity, right? In fact, for us, we have n equals 100. And so if you want to be precise, we shouldn't say equals, we should say approximately equal to. Okay? But we'll just, all right. So here's the question. So looking at those numbers, what is P of A? So pause your video and figure it out. All right, I'm sure you can figure it out. So the number in A is 45. All right, so I really should say approximately equal to, and maybe I will for a while, but eventually I just say forget it, just put it equals. So the PA is 45, right? That's the number in A, and the total is 100. Okay? So that's what it is. What's PB? What's the probability that something will land in B? Well, there's 35 in B, and there's 100 total. And of course, what's PC? Political correctness, just kidding. 20 over 100. All right, how about this? What's the probability A or B? So probability A or B, that's the same thing as PA plus PB, and that's 45 over 100 plus 35 over 100, which is 80 over 100. How about P, B, or C? Well, you can kind of do it in your head, right? It's 55. 55. See, I'm getting slacky already. 55 over 100. How about P, A, or B, or C? What's that? It's 100 over 100, which is 1. Okay? All right. Now, so I think that's fine. But we got to go more than that. So this is 0.45. Okay. So in this experiment, the probability that something's going to land in A is 0.45. Okay. Now, let's say we throw, let's say it's darts, 1,000 darts. Okay, 1,000 darts. How many do you expect to land in region A? Well, if the probability is 0.45 and you throw 1,000, it's just 1,000 times 0.45. Okay, so that kind of makes sense, right? So 0.45 times 1,000. And that's, 450, right? 450. Okay, that makes good sense. Now, but let's write, what is this? Okay, this is the probability, right? This is the, all right, hold it. So the number that you expect, so NA expected, right? Let's call it an expected value. Expected value. So the expected value, NA expected, is just equal to the N, that's the number that you throw, times the probability that it's going to go in A. All right? So this is a big deal. makes perfect sense, but you want to remember it because we're going to use that later on in a different, slightly different form, right? So the number that you expect in region A is the total number that you throw times the probability it's going to be in A. All right, what is N, A, or C expected? If you throw 1,000, you're still throwing 1,000 darts. Well, A or C, the probability A or C, 45, 20, that's 65, so it's 0.65. So it's 1,000 times 0.65, which is 650. So that's called expected value, right? Expected value, the probability times the total number that you throw. All right, so there's your quick review of probability. Now let's get back to photons. Let's get back to photons. Double slit. That's all we ever talk about. Double slit, right? Quantum mechanics. Oh yeah, here it is. So NA expected is NPA. All right, I already said that. All righty. Double slit. Just look at this. So like it says, photon arrival positions. Now, you know, this is all you see on the screen, right? All you see is this, you know. And so if that's all you see, I mean, what can you calculate? You know, you're doing this double slit experiment with a beam of light, and you're seeing that some photons land there, nothing lands there, some there, nothing, something, and da-da-da, right? And so what can you calculate? I mean, do you know which photon goes through, lands where? I mean, and you know there's a certain probability going to land here, there, but nothing's going to land there and there and there. I mean, so what can you calculate? What can you calculate when you do a double slit with light? Probabilities. So that's all I can calculate in quantum mechanics, probabilities, which is completely contrary to classical physics, right? I mean, you don't say something in classical physics, you know, what's the probability that if you throw something, it's going to land in a certain place if you have a certain initial velocity and all that? Come on, probabilities, you crazy? But in quantum mechanics, all you can calculate, probabilities, okay? In other words, you have no idea, well, I mean, we've got to be careful. When you do the double slit with the photons, all you can say is it's going to, you know, just highly probable that's going to land here, 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 here. Well, that's all you can say. Sorry. And again, you know, it's not going to land there, there, you know. Probabilities, all I can do, probabilities, okay? So that's why we had to review probability, all right? Okay, so now we're going to talk about this expected value business with photons. And I remember, you know, years ago when I started teaching using this book, I thought, oh my goodness, Randy Knight, your notation is incredibly cumbersome. How can you do this? But over the years, I realized it's wonderful because, yeah, it's kind of cumbersome. You know, you have to write a lot and everything, but you know exactly what he's talking about, you know? And so it's incredibly clear. So it's great. So I like it. Now, all right. So expected value, N in delta x, that's a width, right? So you're trying to figure out the expected value in a little width at some particular position x, okay? So the number of photons in this narrow strip when it is at position x is written as n, the number of photons in delta x in this width at this position x. Got it? I mean, that's what it means, all right? A lot of books, they would just say n, and you say, what is n, you know? But this is incredibly clear, you know? Number of photons in this width at this position. Bingo! That's what you mean. That's what n is. So it's an expected value. All right? And wow, look at this. Expected value is the total times the probability. The expected value in the width at the position x is the total number times the probability. And don't just write probability, just write probability in that width at x. So like I say, cumbersome but clear. I hope it's clear anyway. So here, look, let's do some examples. So here, all right, let's see. So here, the probability, okay, so we want to figure out the probability that whatever the photon is going to land in this width, delta x, at this position, x1. Okay? So you go to x1, there's the width. So you count. Well, they already did it, right? So the number in this rectangle, right, with this width at this position is 12. Now it says that the number total is 18. So the probability, of course, is just the 12 divided by the total, which is 18, which is 4 over 28, whatever. Okay? All right? And here, the probability that something lands at x2 within some width. I mean, you have to say a width, right? So it lands at x2 within some width. 1, 2, 3, 3 over 84, which is a 12, 1 over 28. So that's just the probability, okay? And then if you, well, okay. Let's see here. All right, and then, you know, if you wanted to calculate the expected value, you know, you would just multiply the number times the probability. All right? So, well, I mean, they did it. Okay, sorry. So the expected value here, I mean, we calculated the probability, right? It's 12 over 84. And then the expected value would be the total number, 84, times the probability, 12 over 84, so you get to 12, right? Here, the expected value at x2 is the total number, 84, times the probability, 3 over 84, so you get 3. I mean, it's just this, you know, it's not a big deal, it's just that. Okay, so I'm just repeating myself, right? All this fancy business is just what we had earlier. But it's going to get more complicated. All right. Okay. So let's look at these last two plots. So here's the interference, right? That's the cosine squared. Remember that cosine squared? The intensity, the amplitude squared from the wave, from double slit experiment. And then here we see the photons, right? Okay, so we see intensities and we see dots. So they have to be related. Okay, I don't usually like to do really long derivations in class, but this is one of these times where I have to. So slap your arm or something, make sure you're totally awake, because this is going to be long, but you have to understand the steps. I mean, that's why I'm doing it, okay? So here we go. So what we want to do is we want to get a relationship between the intensity from the waves and the dots. All right, that's what we're doing. So here you go. All right, first of all, what's intensity? Intensity is power over area, right? Remember we learned that, I don't know, a long time ago. Now what's power? Power is the change in energy over the change in time. Yeah? Okay, now for us, what's area? You know, what's area? Well, remember, we're looking at the screen, you know? And so what we're going to say is that the area is the area of this rectangle. It's that width, delta x, that we can keep talking about, times some height. And you're going to use uppercase h. Why? Because lowercase h is Planck's constant, and you don't want to get those confused, right? So uppercase h for height. So the area here is just h times delta x. So area is h times that delta x. And they write delta x like that because it's supposed to be small, all right? That's kind of why they do it. All right, now we want to keep this simple, you know? So we're just going to say in 1 second, all right? So we're just going to say 1 second, so delta t is 1, so we keep it simple, right? All right, so in 1 second, the expected value, now we're going to talk about energy, all right? Not just number of photons, we want to talk about the energy of the photons. All right, might as well. I mean, come on, that's what this is, right? This is energy over time. I mean, sorry, this is energy over time, that's area. So we're just going to say that the time is 1 second, so basically the power is the energy. That's really what we're, all right? Power is the energy, because it's just 1 second. All right, so we're going to say that the expected value of energy in the width delta x at some value x, all right? Okay, now what is that? Well, again, this is energy, this is area, this is intensity, right? And so the power is the energy because we said the time was 1 second. So the energy is just the intensity at x times the area. Woo! All right? That's all right? So all we're using is this, but we're kind of cheating a little bit because we're just saying that the power, instead of just saying delta E over delta T, we're just saying delta T is 1 second, so power is just delta E. We're just calling it E, all right? So this is basically we're saying I equals E over A. That's sort of what we're saying. So expected value of E in delta X at X is just intensity at X times that area. That's okay. That's not so bad. Now, energy, right? Okay. But we also can just look at the number of photons, right? So the number of photons in that rectangle in the width or within the width delta x at x. And what's that? Well, wait a second. Every photon has energy hf, right? Yeah. So we can get the number of photons just dividing the energy by hf. Agree? I mean, that makes good sense. So let's just do that. So the number is just the energy within the width delta x at x divided by hf. Yeah? This is the total energy. This is the energy per photon. So this is the number of photons. That makes good sense. And again, the energy is just the intensity at x times A. So we have to divide by hf. All right, now we got to get probability in here somewhere, right? Right? We're going to get probability. Let me show you where to get that from. So, come on, where are you? Yeah. So we want to get probability, okay? So the probability that a photon lands here, you know, in this rectangle, just what it says over there, right? The probability in the width delta x at some position x is just equal to the expected value n in the width at x, right, divided by, so the probability is just this divided by n. Now you got to be careful, right? This is the expected value in delta x at x. But we're going to divide, hey, I'll do this. Maybe that'll keep it simpler, right? Then if I just write n, you might be canceled to do that, but that doesn't make any sense, right? Because this is connected with this. So I'll just say n total, right? So this n, I'm just going to write it as n total. Keep it, make it nice. All right. Well, what's that? Well, n in delta x at x is equal to this. So I'll write that. Because remember, we want to connect the dots with the intensity, right? This here is dots, right? This is intensity. So intensity at x over A, and then hf, but then we have to divide by n total as well. That's an n total. Okay, so that's not so horrible. Now, earlier we learned in a different chapter, but we talked about this a few minutes ago, that the intensity of a wave is proportional to the amplitude squared, right? All right. Well, I guess I could write that better. I should really write it like this. The intensity at some point x is proportional to the amplitude at some value x squared. All right, that's really what I should write. All right, that's cool. So then, I'm running out of room. I wish I was in 132. So then, look, if the intensity is proportional to the amplitudes, okay, oh my gosh, we got to be careful. We got to super be careful. All right, let me get rid of this A, because this is supposed to be area. So I'm going to write H delta X. H delta X. Too many A's, huh? All right, now, I is proportional to the amplitude squared. Here's I. So I'm going to say that is proportional to the amplitude squared. Now notice, I just wrote proportional. Now what happened to the H, you know? Oh, I forgot the dx times dx. Okay, so the I is proportional to ax squared. So I put I proportional to ax squared. Okay, h is just a dumb constant, so goodbye. Delta x is, I got to keep that there. N total, that's an n. That's a constant, go away. Planck's constant, go away. F, go away. Because remember, it's proportion, so I don't need to write down constants if it's a proportion relation, right? All right, so now I have, this is perfectly legal as long as I just have a proportion sign. Okay, so then, now I got to erase some stuff. Okay, so I have the probability in delta x at x is proportional to ax squared delta x. I'm going to divide this by delta x, and I'm going to divide this by delta x. So I'm going to forget about this stuff. Okay, so it's totally legal what I did. So let me write it up here. So I have the probability in delta x at x divided by delta x is proportional to a amplitude squared. That's it, times delta. Okay. All right, now, is everybody okay? I hope you're okay. Okay, now this is not just algebra, right? This is a physics class. Okay, what is this? The probability in delta x at x divided by delta x. Is that wave or particle? Well, this is particle, right? I mean, that's, photons, dots. So this is particle, right? So that's particle. And what's this? The amplitude of the wave squared. That's wave, right? That's wave. So look at what we just did, okay? What we just did is we figured out a relationship, and we figured out how we can incorporate the wave model and the photon model, or the particle model, right? Photon or particle model, wave model. Now we still have a long ways to go, but we're getting there. All right. Now, this is just the amplitude of the wave squared. Whoopee. What's this crazy thing? So what is this? It's the probability, percentage, right, divided by a width, like in centimeters or whatever unit you want. So we got to come up with a name for this. The probability divided by a length. Okay, what are we going to call it? Right? What are we going to call it? I know it has to do with particle, but we got to give it a name. You know, so what are we going to call it? Well, go back to the wave chapter, traveling waves. We talked about a wave on a string, remember? And we had that the velocity of a wave on a string was equal to the tension of the string divided by the mass density, right? Remember? Mu was the mass per length. Okay, now, you know, for all of the cases that we had, this was constant, right? So that was nice. But, you know, oops. Yeah, but what if the string was like that? I mean, you know, the mass per length would not be constant, correct? And so, you know, you couldn't just say constant anymore. In fact, you'd have to do something like this. You'd have to say that the mu is a function of x, right? The mu depends on x. It's not constant. I mean, you can still call it the, you know, you can still call it the mass density, right? It's still the mass per length. It's just that it's not constant. Who cares? It's still the mass density, you know? All right, so we have mass per length was mass density. So here we have probability per length. So what are we going to call it? You guessed it. We're going to call it probability density. All right? It makes good sense, you know? It's probability per length. So probability density, okay? Probability density. If you want to be fancy, you can say linear probability density. I don't care. I just call it probability density. Okay? Yeah, most people just call it probability density because we're lazy, huh? Okay, so don't forget. So this is not just a probability, you know, some kind of, you know, a fraction, right, or a percentage or something like that. This is the length. So this is the P of x. It's the probability per length, probability density. Don't get them confused. If you're going to get them confused, oh my gosh, this chapter and next chapter is going to be a total disaster, all right? So this is what's nice about it. When we mean probability, we will always write out P-R-O-B, you know, probability. When we mean probability density, we'll be lazy, just P of x, okay? That's all there is. All right, so wonderful. So what does this equation now become? What does this equation now become? Well, this is the probability density that we decided to call P of x. So we have P of x is proportional to the amplitude of the wave squared. And again, this is the particle, right? Because there's dots, right? It's dots on the screen. And this is the wave, right? It's the wave amplitude squared, which is intensity. So there you go. So that's what we wanted to do, is connect the wave and the particle models. Well, we did it. All right, we did it. So this is a super big deal, and we're going to use it a lot in this chapter, next chapter. Probability per length, particle proportional to the intensity, right? That wave amplitude squared, right? Probability density proportional to the intensity. Particle wave. Super important. How many times have I said it, right? All right, let's quit because you're going to do some work right after we come back.